Let's now do some examples of finding some lengths of curves. So we've got a curve as defined by this, and we're interested in finding the length from x equals 1 to x equals 5. So in that case, that length is going to be equal to, generally, we're going from x equals a to x equals b, and we have the square root of 1 plus dy dx, and that's squared dx. Now, I just wanted to note about the formula sheet. The length for when we're looking at the parametric version, that does appear on the formula sheet. However, when we're looking at it in terms of x or y, it doesn't appear on the formula sheet. However, it kind of does in disguise. If you look at the surface area formulae, which we haven't done in class yet, we're going to be doing for our next lesson, the surface area formula contains, if you look here and here, that square root that we're expecting. You just remove the 2 pi and either the x or y, and that will give you the length, whether you're looking at movement in the x direction or the y direction for your terminals there. In putting on that 2 pi either y or 2 pi x, that then changes it into a surface area, which I think will make a lot of sense when we get to that. So just note, these formulae don't appear on the formula sheet as you might expect, but they do appear within another formula. So to be able to do this, we need to know what dy dx is. So starting with this, and we're going to differentiate with respect to x. So that means dy dx, well, this could have been written as, we could have had a half x cubed plus 1 over 6 x to the negative 1. I think that'll make life easier. So that makes dy dx, looking at that first term, half x cubed, that's going to become 3 over 2x squared, bring the power down the front, take 1 from the power, and then we're going to have minus 1 over 6 x to the negative 2, because we brought that original power, negative 1, down the front, and then we subtracted 1 from the power. And if you wanted to rejig that to have it without negative indices, you could write that as 3x squared over 2, or just leave it as 3 over 2x squared, either way, and then minus 1 over 6x squared. So let's go ahead and put that into this formula. So we're interested in going from x equals 1 to x equals 5. And that's what allowed us to find out which formula we were using. We needed the one that had the dx at the back because we're interested in how x is changing. And then we've got the square root, and then 1 plus, and this was dy dx, so we're going to put that inside of our brackets and square it. Okay, now it's going to be a little bit of algebra. If this work has allowed, you could pop that in as it appears there. But let's pretend this is a paper 1 question. So if we expand out that central term, we would have, let's pop in a big square root, 1 plus, squaring that first term, we're going to have 9x to the power of 4 over 4 minus 2 lots of 3x squared over 2 times negative 1 over 6x squared plus, let's square that, 1 over 36x to the power of 4. Oh, didn't need to increase that, that was almost bang on. And then we're going to have dx. Bit of cancelling that we can do in this central term. Those x squareds cancel out. So that means we're just going to be left with a half there. So if this is half, and we've got that's negative, and we've got that 1, that means, let's put that 9x to the 4 over 4, and we'll put the 1 over 36x to the 4. So that 1 minus a half will just become plus a half dx. The square root was a little too large this time. So let's continue here. So I think our best course of action is to get that all over common denominator. And I am hoping that this is going to be something nice that's something squared because it's inside of that square root. And I think you find if you're doing a question like this by hand, you're often going to have square things so you can remove it from that square root. If not, you would just need to use methods of integration, possibly use substitution or something like that to make it work. But I think we can just do this directly. So common denominator there, the lowest one we're going to have is 36x to the power of 4. So that's going to make the first term 81x to the power of 8. Then we would have 1, and then that 1 over 2 will become 18x to the power of 4. Okay, I notice inside of there, if I factorize this numerator, if you preferred, you could write that as 81x to the power of 8 plus 18x to the 4 plus 1. But factorizing this, let's pop that square root, oops, and we've got a dx here. Have we forgotten any others? No, we've got them all. I'm going to pop that there just in case I forget. So factorizing this, I could actually write that as 9x to the power of 4 plus 1 all squared. And on the bottom, if I wanted to, I could write that as 6x squared all squared. Meaning, when I take the square root of that, we're just going to have 9x to the power of 4 plus 1 on 6x squared dx. If we wrote 9x to the power of 4 on 6x squared plus 1 over 6x squared, now we're getting somewhere because we can simplify down that first bit. That would become 3x squared over 2, and we'd have plus 1 over 6x squared. Popping on our dx. And now we're at the point where we can nicely evaluate them. So we'd have 3 over 2, add 1 to the power, becomes 3, divide by the new power, so that's going to be times 1 over 3. And then for this term here, that's 1 over 6 times x to the power of negative 2. So because we have to add 1 to the power, that would become x to the negative 1. So we'd still have 1 over 6x, because 1 over 6x to the negative 2, adding 1 to that power would make it 1, which is equivalent to this. And when we divide by the new power, dividing by negative 1, gives us a negative there. So 125. Simplifying things down a bit before we substitute, x cubed over 2 minus 1 over 6x. Now we're going to sub in that 5 and that 1. So that would become 5 to the power of 3 on 2 minus 1 over 6 times 5 minus 1 cubed over 2 and then minus 1 over 6 times 1. So we've got a half minus a sixth in that second one, and doing the arithmetic with all that, we should get 932 over 15, and that will be units. It's just units, not anything like units squared or units cubed, because we are finding a length. Now, doing that on your CAS, whether you're using the TI or the Casio, is much more straightforward. So you can either put this in using the formula that we did before and doing the integral, or you'll notice on both the TI and the Casio there is an arc length, meaning arc length formula, and you put in your original function here. So not the rearrangement of what we had here, although you'd certainly be able to put that in just fine, but you would actually put in the original function, you'd tell it, so the syntax is then, you tell it which variable you're interested in, and then going from where to where. So if you have a look on the Casio, you could of course go to action, calculation, line, and arc length, but then you do need to remember the syntax. So if you didn't want to do that, you could go to interactive, calculation, line, arc length, and then it's going to ask you what to put in. What it might be more useful to do though is to actually type the expression in the main menu first and then highlight it and do interactive. But you'll see it helps you get the syntax correct. It's asking you what variable, the start point and the end point, and that will calculate it for you nicely. So you can either do what we did, although this one you'll notice it is the rearrangement when we got to this point here, which is totally fine, but if I were you, I would have put in this line here because that avoids a lot of unnecessary algebraic rearrangement on a paper 2 exam. So you've got those two options, either popping that as is into your calculator or using the arc length situation and putting in your original function, telling it you're looking at the x variable and going from 1 to 5. So in this question here, we've got a new function and we're told that we're just going from, apologies for this, we're told we're going from x equals 0 to x equals 2. We want to express that as a definite integral and then hence calculate the arc length, giving your answer to 4 decimal places. So for this one, it's just testing your ability to apply the correct formula. So let's put the general one in first. I find it helps me collect my thoughts. So 1 plus, and we've got dy dx, which we're squaring, and then dx. So for this particular one, this is the definite integral part. So this is step 1. So we need to show that it's going from 0 to 2 because we're interested in how x changes. Then we've got the square root of 1 plus, if this is f of x, that'll be equal to y. So dy dx is just going to be 4x to the power of 3. So then we'd have 4x to the power of 3, square it, dx. And just because this thing's easy to evaluate, I think it wouldn't hurt to do that. 1 plus 16x to the 6 dx. Let's put this one into our calculator and get it to 4 decimal places. So let's try those two techniques that we just spoke about. Let's do it doing just the integral. That would be from 0 to 2. And we've got a square root, 1 plus, and if you so desired, you could just pop that in as 4x to the power of 3. And then square that, dx. So to 4 decimal places, we'd have 16.6469. And we'd put units. Now let's try using that arc length thing that we looked at before. Okay, so I've put in the x to the power of 4. This one's not super hard, so I don't think it would have been difficult to go to calculation, line, arc length. This one wouldn't have been hard to type in there. And we're going from 0 to 2. And okay. And we get the same expression. So either of those may have been faster or slower for you. Good to familiarize yourself with either. I think this one is particularly good if you're in a multiple choice situation and you want to quickly find the answer. This one's good if you are doing a little more working out, perhaps one of the shorter extended response answers, and you need to actually show what formula you've applied to be able to find this. Okay, we've got an exam 1 question here, so going to be doing this one by hand. We're interested in finding the arc length of the curve y equals 1 over 3, and then in brackets x squared plus 2, all raised to the power of 3 over 2, from x equals 0 to x equals 2. So we again know we're using that version of the formula that has a dx at the end. Now, in order to apply this formula, we're going to have to know what dy dx is. So to do that, we're going to have to use a little bit of the chain rule. So let's let u be what's inside of that bracket, x squared plus 2, meaning du dx is just going to be nicely 2x. Then that means that y would be equal to 1 over 3 u to the power of 3 over 2. So dy du would be a half u to the power of 1 over 2. Because we're taking the power down the front, taking 1 from the power. So therefore, by chain rule, dy dx is equal to dy du times du dx. Let's put together those two things we had before. dy du we said was a half u to the power of a half, and du dx was 2x. Now we've got a half u to the power of a half. Oh, I notice we've got a half and a 2 here, so let's get rid of that. U to the power of a half would be square root, and let's put this x here. And then we'll have the square root of our original value of u was x squared plus 2. So that's dy dx ready to go for our formula step for the arc length formula. So therefore we have L, and let's write the general form before we get into all of the algebra that we're going to do. 1 plus dy dx squared dx. So for this question here, they told us we were going from x equals 0 to x equals 2. We've got 1 plus x square root x squared plus 2, square all that, dx. So let's neaten this up a little bit. We're going to have 1 plus, and then the thing in brackets is all squared, so we can make that x squared, and then in brackets x squared plus 2, because that was originally inside of a square root. Okay, let's expand out that bracket. Everything's still inside of that square root, and as I said, often with these questions we're going to be ending up with something squared inside of that square root. So expanding that bracket, I'm going to put this bit first. That's x to the power of 4 plus 2x squared plus 1 dx. And that's really nice, because inside of that square root, when we factorize it, that's just x squared plus 1, all squared. So I'm showing lots of lines of working out here. That's of course not necessary for you to do. it is still important to be able to communicate. So there are some lines you could skip, but I wouldn't go straight from like this line to our answer line. It's often said that you need to show a reasonable path towards your answer. So showing working out is part of your communication. So that's now nicely evaluated. We're going to have x cubed over 3 plus x. Terminals are still 0 to 2. 2 to the power of 3 on 3 plus 2, and that would just be minus 0. So that's 8 over 3 plus 2, which becomes 14 over 3 units. So a note from the assessor's report. It said that there were errors in the formulae. Now it says despite it being on the formula sheet. It's hidden within that formula sheet. So it is there, but it's within another formula. Some people found the derivative correctly, but some made errors leading to an impossible integral. Some gave the derivative as this, and we found unable to recognize the perfect square inside of the square root and therefore had difficulty continuing on. Really important to follow all of the steps that we've talked about there. Let's look at another exam question now. Okay, in this one here, we now have some parametric equations, which are totally fine. We've met lots of parametric equations before. And this one, as we saw, is nicely on the formula sheet. So just make a note, it's from A to B. And inside of our square root, this time we have dx dt all squared plus dy dt all squared. And that's going to be dt. So you'll notice they've told us where t needs to be in between, whatever parameter we're using. So that means we need to know what dx dt and dy dt is. So x is here, so dx dt just means we're differentiating this with respect to t. And that's nice, it just becomes 3 cos t. And this one here, that's our expression for y, so dy dt, cos goes to negative sign, so it would be negative 4 sine t. So, what happens then? T we said was going from 0 to pi, because remember we had a dt on the end here. We've got our square root. And now dx dt was 3 cos t all squared, and plus negative 4 sine t all squared, because that was dy dt. Now, I notice with this question, it doesn't have the final answer. It's got expressions, so it's given by what? None of it looks quite like what we've got at the moment. This one here is a relatively good distractor because it's got the 3 cos t and it's got that minus 4 sine t, but it's forgotten the squares here. Also, this one, relatively good distractor, but you'll notice that 3 and that 4 hasn't been impacted by these squares, so another really solid distractor. So we're going to have to do a little more manipulation to get something that looks familiar. So let's perhaps distribute out that square. So we've got 9 cos squared t, and then we've got plus that negative 4 squared will be 16 sine squared t dt. So we have a look at A, and that looks pretty close, but there's that negative there. So what have we gotten rid of so far? A, we said didn't work, D, and E. So looking at B and C, it looks like there's still going to have to be a little bit of manipulation to do. Whenever I see cos squared t's and sine squared t's together, I always think, I know that cos squared t plus sine squared t equals 1. So let's maybe be a bit creative with that. Let's write this as 9 cos squared t plus 9 sine squared t plus, if I wanted to get to 16, I need to put a 7 sine squared t dt. So that means here we can factor out that 9, and that would be cos squared t plus sine squared t plus 7 sine squared t dt. So this is just going to be 1. And if you have a look at option B, we've got 9 times 1, which is just that 9, and that plus 7 sine squared t that we had down here. So option B is correct. So the next question is another VCAR 1, 2020 Exam 1, question 9. With part B in particular, you can see that 41% of students got 0 for this problem. So this one is a little meatier. It's only worth 3 marks, and I found I had to do quite a bit of working out to be able to earn those marks, but let's talk through it now. So we have another example of parametrically defined curves. We have x equals arcsine of t, And we've got y equals log base e of in brackets 1 plus t plus a quarter log base e of in brackets 1 minus t. And we're told t goes in between 0 and 1, not inclusive of 1. So it says dy dt, all in brackets squared, can be written in this form here. And it says where a, b, and c are real numbers, show that a equals 1, b equals negative 2, and c equals 16. So we're going to have to start with part A here. So we want to find dy dt. And as we said, y is given by this. We've got some lovely logs here. So when we differentiate this log based e of 1 plus t is just going to become 1 plus t. And then we're going to have minus 1 over 4. And then we're going to have 1 over 1 minus t. Now, it's important to note here that what we're asking for here is dy dt squared. It's not asking us for the second derivative, so really important to be aware of notation here. We are going to neaten this up, we're going to square it, we're going to write it in that form, and we're going to show what a, b, and c are equal to. So let's square this. So I've just put this negative here, because when I multiplied this term and this term together, this negative was there, just in case you're wondering where that came from. Now, you might be tempted to expand something like this out, but if we look at the form they're interested in, they've got that in brackets, everything here, in factorized rather than expanded form. So let's not expand that out. Let's neaten this up and get towards getting to this form. Now, I do notice with this one in here, notice this is 1 minus t squared, and here we've got a difference of perfect squares situation. So for this one, we are actually expanding it out because we're trying to get it in a particular form. So that would be 1 minus t squared there. So 1 minus t squared, not 1 minus t all in brackets squared. And then we've got plus 16, 1 over 16, sorry, 1 minus t all squared. Okay, now we've got it in this form. We can now see a needs to be, well, just 1. B needs to be negative 2 because we did assume a positive here. And we've got C needs to be 16. A is equal to 1, B is equal to negative 2, and C we said was equal to 16. Because I'm fancy, let's put a little therefore there. So there, we've shown the values of A, B, and C as required here. Okay, let's get into part B where we're actually finding the arc length, which here they've called S, from the curve from t equals 0 to t equals a half here. And we want to give our answer in a particular form, so that's going to be something that we're going to have to refer back to. M, N, and P are all rational numbers. We've already got dy dt, because you'll notice I've normally done L, but they've asked us to do S. Either is fine. So we're going from A to B. We're interested in dx, square root, there we go, dx dt all squared plus dy dt all squared, and we're doing that with respect to dt. So if we look at x, dx dt is just going to be 1 over square root of 1 minus t squared. That's one of our nice standard things when we've got arc sine of x. So we previously had dy dt here, so let's now put it all together. Now, as we've seen in previous questions, because everything is currently trapped inside of that square root, we're going to be manipulating what we have to attempt to get a perfect square inside of those brackets. These questions are purposefully written so we can use that. You'll also notice that I've kept this in the form that they had suggested in the question in part A, rather than putting it into another form or expanding things out. Often that's because they've told us in part A to write something in a particular form because it's useful. That may not be the case too. They may have done part A as they've done, show that these values are equal to this, so that if you couldn't do part A, part B was still accessible to you. So I'm going to use it in the form that they've given me. Perhaps it's a useful one, but just keep in mind, sometimes it's because it's useful, sometimes it's because they want to be able to make sure you have the answer to part A so you can still actually attempt part B. We'll see how we go with it. I've just realised I've accidentally popped a square on this one here, but remember that was dy dt all squared already. So that's nice. I was really worried I was going to have to do much more algebra there. So let's square out that first bracket. In that case, we're just going to nicely have, let's pop that square root there ready to go, and the dt so I don't forget. So that becomes just 1 over 1 minus t squared. And then we're going to have plus, and we're going to have everything that we originally had inside of that second bracket. Okay, really nice thing to notice here. We have this, and we have this. And these two, if you do one minus the other, it's like we've got, if we call this a for a moment, then this expression here would be minus 1 over 2a. So a minus a half a would just be equal to a half a. So let's put them together in the next line. Okay, I really feel like we're getting somewhere. With that 1 minus t squared form, let's now write that as 1 minus t, 1 plus t. You'll see why in a moment. And I'm also going to put this term first. The reason I'm doing that is I am trying to get to some point where I have a perfect square. And I notice if I have, again, square root, that 1 over 1 plus t squared, I could have really written that as everything squared here instead of that square at the bottom. Then I'm going to have plus 1 over 2, 1 plus t, 1 minus t, and then we'll have that 1 over 16, 1 minus t, all in brackets squared. This is a perfect square, I know. What a relief. How do I know it's a perfect square? Well, you could do a bit of algebra, but I've done it by observation. I see if I have 1 and then 1 plus t, if I square that, it's going to give me this term here, and I can see it appears in this term here. And that means my second term is going to have to be plus 1 over and then 4, 1 minus t. And that's going to be in brackets squared. Reason being, it needs to be the square root of this one. And I can see if I do this times 2, it gives me this entire term here. So that was really important to be able to find that perfect square, because that allows us to do this. So we get rid of that square root, 1 over 1 plus t, and then 1 over 4, 1 plus t, 1 minus t, dt. Now we can actually evaluate this. Whew, we're nearly there. So this one is just going to be log base e of the magnitude of 1 plus t. And then we're going to have, because we've got 1 minus t in there, minus 1 over 4 log base e of 1 minus t. And we're evaluating from 0 to a half. Popping all that in, this one you're going to have, when you're putting in the half, 1 plus a half, and then 1 minus a half. And when you put through the 0, you're just going to have zeros. So let's perhaps squeeze it over here. That becomes log base e of, don't need the magnitude because 3 over 2 is already positive, minus 1 over 4 log base e of 1 over 2. Now on that you might think we're done, but recall we needed to have our answer in a particular form. We needed 2 logs and we needed them added to each other. Totally okay for m, n, and p to be rational numbers, so we don't need to use any log laws to prevent that if needed, but we can use log laws in order to ensure we have 1 log plus another log with a coefficient out the front. So we're pretty close. That first log term's looking fine. Don't need to do any manipulations there, but I do need to change this to a plus. So to make that work, I'm going to use the fact that I know 1 over 2 is equal to 2 to the power of negative 1. So I'll do an extra step. And then 2 to the power of negative 1. And then we're going to bring that power out the front using the log laws. I know at my school we call it plugging. So that becomes plus a half 1 over 4 log base e of 2. So now it's in the form that we required, and we've finished this question. So as you saw, quite a lot to consider here. We had to be really careful with our algebra, and please still check, I may have made an error. But using that form that we had, showing things in a particular form that VCAR is asking us for, and being really careful with our algebra can let us be one of those students that gets 3 out of 3 for this question. Still feel like it was a lot of work, and you can see, yep, that's the version that we had at the end. We did need to show that final step though, and I think that's where a lot of people would have gotten 2 out of 3 rather than 3 out of 3, not writing that final step.